Welcome to GIS, and welcome, remotely or otherwise, to the campus and grounds of the University of Maine at Fort Kent. We're going to start today exploring the data types that you will encounter in this class, and those are raster and vector data sets. This air photo is an example of a raster data set, or a gridded data set, meaning that if I zoom in, for every one of these 60 by 60 centimeter squares, or pixels, there's a value. The value is a mix of red, green, and blue color bands, which together make the color you see. As you zoom out, you can see features on the ground. As you zoom in, you see the underlying data, which is all just square after square after square after square of cells or pixels. All of those are the same, grids, cells, pixels, all used interchangeably. And these ones happen to be 60 by 60 centimeters, or about 2 feet by 2 feet. The digital elevation model, or DEM, is another very common raster type. So I'm going to turn off the air photo, select the elevation model, and what this is a 10 by 10 meter pixel size, where every 10 by 10 meter cell has the value of elevation above sea level. If I use my Identify Features tool, I can click on this, and it tells me that this is 155.84 meters above sea level. This one is 158. This one is 152. Now I'm sure you've noticed as I zoom in and out, the colors change, that this pixel is not always the same color. As I zoom out here, this is now the brightest white, and that is the darkest black. That's because I've set this model to show me the lowest and highest elevation within this view, no matter what I do. So as I zoom around, that's the hill, that's the St. John River, that's the Fish River. So I zoom out, there's more context. There's higher hills that take up that white color. If I want to move, I can use this pan tool. Click, hold, and drag. And now there's Katahdin. Everything in the context of Katahdin looks pretty drab, where here at Baxter Peak, we have the highest elevation. And if I zoom all the way in here, I can look around for the high point. That looks like that's the one there. I can use my Identify tool and see that we have about 1,603 meters above sea level. So the fundamental concept of a raster is that you have a grid of cells, or pixels, where each pixel or cell has one value. And that value can be elevation, or it can be a color defined by the mix of red, green, and blue. And you can do an awful lot with a digital elevation model, or DEM. And the first thing you might think to do is the slope. And we can see that there's a change in elevation here. We would like to know the rate of that change. We have a cell here and a cell here, and we can compute the difference between this one and that one. That's called slope. So let's check on our slope model and check off our elevation model. And the way I've got this set up is to show if the slope is less than 2%, meaning that for every 100 feet of horizontal distance, you have 2 feet change in vertical distance. It's going to be colored blue, meaning it's pretty flat, water might collect there. Green, as we see here, relatively flat, between 2 and 10%. Yellow, 10 to 20%. Orange, 20 to 30%. Red, potentially dangerous, over 30% slope. And of course, being on top of Katahdin, you're going to have a lot of very steep slopes. So there's the tablelands, it's relatively flat. There's the knife's edge, where you would perhaps go hiking if you're feeling particularly brave. And then as you get into more of the general landscape here, this is where all the bugs come from. And if we zoom out, we can get a feel for the entire landscape. It's going to take a minute to draw. I'm going to pan using the pan tool up to northern Maine. And we can see this central ridge of hills with lower elevation down here and more flat ground. So more steep ground running down the middle, more flat ground here. Let's zoom in on that. So here we have some of the larger lakes here. We know these are lakes. Not all these blue areas are lakes. These are areas of flat ground where water might collect, but I know there's a lake here. And if you're ever questioning, the best thing to do is usually to pop off whatever models you're using and turn on the air photo. So there's something more familiar. There's Fish River Lake. So let's go back to our slope model here, check that back on, and we can zoom right in here and see that if we're to be working in here, we might want to not have a machine going in to operate on that. 30% slope is beyond the design capability of some machinery. You might have a dangerous situation or an accident. Contour lines are the other way to display elevation and also gives you an idea of the slope. So let's just check on this contour line here. And we can see that every one of these lines represents a constant elevation. And in this case, every 10 meters elevation change gets a line. So if you were to walk straight along one of these lines, you would neither gain nor lose elevation. If you were to go directly perpendicular, you'd be walking straight up and downhill. And you see the closer these lines are together, the steeper the slopes are. So if you choose to display in this way, you can see both the absolute elevation here, this is the peak of a small hill, and that is the slope approaching that hill. We can also tell something about the aspect here, that this is a north-facing slope, and we know that the sun at noon is down here in the south. If we scratch our heads and say, well, a north-facing slope is going to be a shadier spot, perhaps the deer wouldn't want to hang out there in winter, but the south-facing slope, well, that's going to be directly getting a whole lot of sunlight. We can sort of figure those out looking at contour lines and slope models. Later on in the class, I will show you how to use the direct solar radiation tool, which actually gives you some information directly about that. So we can see on July the 31st how many hours of sunlight each location is expected to have if it happens to be a sunny day. So that would be in shadow most of the day, and this would be in more direct sunlight. So we can again use our Identify Features tool, click on that, and that cell right there, say we're still reading off the elevation model, I need to click on that, so this tool is pointing at that data set. Click there, and that is expected to have 6.5 hours of direct sunlight on July 31st. Now we can see we still have the contours turned on, but we can't see them. That's because this is below that in the table of contents, and this is a solid thing, there's no transparency. If I click, hold, and drag that up above, now it will draw first, so that's on top now. So now I can see how much solar radiation it gets and how steep the slope is based on how close those contour lines are together. So that would be the less steep route, and that would be the more steep route. Now I'll show you one more thing derived from the digital elevation model before I move on. So I'm going to uncheck slope, uncheck direct solar insolation, and uncheck contours, and check on valley depth. And what this is a model created from the elevation model showing how deeply incised or how deeply cut in each one of these valleys is. And that's comparing the lowest elevation down where the streams are up to the highest adjacent elevation. You can see the channel here of the Allagash. Oh no, that's the St. John, that's the Allagash there. There are some lakes and ponds. That gives you an idea of how deeply cut in each one of these spots is. And that matters for some hydrological and geomorphological concepts. Of course, we're getting massively advanced in the course here. I just want you to have an idea of all the fun things that you can do with the digital elevation model. So let's uncheck valley depth, check back on our state 10 meter DEM, and take another look at this. And we can see some of the major influences in the state's geology. So we have a lot of hills up here. We can see some of these ridge lines of where the different parts of the continent came together. We can see about there is where the Appalachian Trail goes. There's southern Maine. Most of our population lives down here. This line approximately here defines some of the major ecosystem type changes where, of course, this being lower elevation and flatter ground tends to be warmer, has a different soil type than over here. So you see differences in agriculture, forestry, all the things that you can do that depend on soil. So again, down here, major changes in elevation. You go up here, it's cooler, you get into a different plant hardiness zone up here. Almost no settlement or no settlement at all in here, except for a few camps on the lakes which are not permanently settled. So we can move around here, and again, this is changing its color as I zoom in and zoom out. And finally, we'll zoom all the way in, see one more time. These are the cells that make up the whole raster model. Every location on this landscape within the range of the data set has a cell, and that cell has one value. One last thing before we jump into vector data sets. I don't want you walking away with the idea that the southern part of the state is boring. If we zoom in here and look at the elevation of down east, there's all sorts of fascinating geology and geomorphology, evidence of the last continental glacier, which melted 15 to 18,000 years ago. the big outwash plains that form the Blueberry Barrens down here, Acadia National Park down here. There's a lot of fascinating geology that just looks like a big black hole if you're looking in the context of the Upper Highlands here. But zoom in, take a look around, explore. With all these things, explore them, enjoy them. There's all sorts of fascinating things you can learn about the state through these kinds of data sets, right down to that esker, which was an old glacial stream. All right, enough introduction to rasters. Let's have a look at the vector data type. So I'm going to check on this data set here, which is the random 95 streams. And those are 95 streams that I randomly selected to essentially take their temperature. And I'm going to right-click and zoom to layer. That shows you the outline of the northern part of the state of Maine. And every one of these 95 streams is one that I randomly selected out of all these streams to take the temperature and ask the question, is this above or below the temperature threshold for brook trout, which is 70 degrees Fahrenheit. So I can use the Identify feature tool here, click on one of those, and that gives me all of the variables that I have in the spreadsheet or attribute table connected to that point. So for this point right here, the stream name is here, fishing, okay, and it is one of the ones that I randomly selected as opposed to one where I was particularly curious about a single stream. That's important in statistical analysis to separate out the randomly selected from the deliberately or thing that might have been chosen with bias. And then I have the ID numbers for the water temperature logger and the air temperature logger that went with it. And I have the northing and the easting, so the UTM coordinates that define that position. And that's an important concept that you see. These are sort of showing as circles, but every one of those, the circle is just a marker. That's showing where the point is. But what it really is a location in space defined by this northing and easting value, where this is 5,221,413 meters above the equator. And it's also about 4,500 meters to the west of a line that we've drawn artificially right up the middle of our UTM zone, which goes about up the middle of the state of Maine. More detail on the UTM system later, but what it really is a way of measuring coordinate locations using a system based on meters. Makes complete sense in terms of ground-based measurements. Displays terribly when you're looking at the entire globe. You can only look at a small part of it at once, but it's a great way of having precise ground-based measurements that connect straight to your GPS. So here's the data that was installed. Here's the fact that yes, it was a randomly selected site. It has been retrieved and measured out. The placement was good. These are my notes on the location. It is a pendant type logger, and we have an average daily variation in temperature, a maximum daily variation in temperature, the number of hours that spent above that threshold of 70 degrees Fahrenheit in July and August of 2019, and the average daily maximum temperature, which is 65.5619193500. So this is different from the raster data set in two very important ways. One, it's just this physical location. It doesn't have any width, length, depth, or anything else besides what's recorded down here in this attribute table. But it has an exact coordinate location. If I wanted to go there, I can go right there, and of course I did because that's where the data set came from. The other important thing is it has more than one attribute, where these grid cells have one value. This is the elevation above sea level. This has a whole spreadsheet attached to it. If I wish to access that spreadsheet, I right-click here and open the attribute table. And here is the spreadsheet. So every one of these is a different point. So point number 79 has this water temperature ID, this air temperature ID, exists 5,168,159 meters above the equator. At that easting, it was recorded on that date. It is in, let's see, I can open that up. Kemquazabamtukuk, I'm sure I butchered that, but took a crack at it at least. Another pendant type logger, and we have the average daily variation in temperature, the maximum daily variation in temperature. Didn't spend any time above the 70 degree line, and was on average the highest temperature recorded in each day was 62 degrees Fahrenheit. So every one of these connects to a point on the ground. If I'm scrolling through here, oh, that was the hottest site there. Let's see, how can I access that? Usually I can right click there and zoom to that, but that is a different software package. So if I want to go here, pan map to selected rows, and there's an example of moving between different software packages. I'm used to using ArcGIS Desktop. We're moving to ArcGIS Pro, and here we're in QGIS. These do a lot of the same things, but they're slightly different. So there is that point, which we recorded over 1,000 hours above 70 degrees Fahrenheit, and the average daily high temperature was 77 degrees, so that is cooking some trout, or the trout would hopefully have been moved somewhere else. So here's our point. That's particularly warm. Let's zoom out a little bit and see what we're looking at. So here we are, and because I've already got this all set up, I can look at the watershed boundaries. And I don't like how that's displaying. It doesn't play well with my elevation model. I can double click on that, and that gives me the option to change. Click here on the simple fill. I want that stroke color, which is that outline there. I'm going to make that a nice bright yellow so I can see it. So there now is the outline of that watershed, and that is all the area that is draining. If I poured a cup of water out here, and if it was to roll downhill, it would eventually land here. Now we can see it looks like there's some sort of areas of the same elevation. What might be going on there? Let's turn off our elevation model and turn on our slope model. There's a lot of flat ground. Flat ground doesn't move water. When water doesn't move, it has the opportunity to be exposed to sunlight if there's not a canopy over the top. I wonder what it looks like on the air photo. Someday that will load. And when it does, I bet we're going to see some ponds there. And if not ponds, wetlands. Ponds and wetlands both slow water down and expose it to solar radiation. And unfortunately, we're cutting straight across a county boundary, and these air photos are given to us by county. So here's the part that's in Aroostook County, but that tells us enough here. That this is a big pond. There's a lot of not moving water, a lot of direct solar radiation on that, and that stream temperature logger is just underneath that big pond. So we can pretty well make a connection here between a warm body of water and a warm stream draining straight out of it. But let's say we want to look at the entire landscape and see, all right, this one's warm, but what other ones are warm? Let's turn off our air photo because that takes a long time to draw. Turn our elevation model back on. Let's right-click on this and zoom to the layer so we see it all at once. And I'm going to turn off these watershed boundaries because we don't care about them at this scale. And see how we still have this one highlighted? I'm just going to click off somewhere else, deselect that. So what I want to be doing here, and see how this one's yellow? That can be a problem here. So let's open up the attribute table again, open the attribute table, and not invert selection, deselect all features from the layer. Selected, 0. Now we're all back to right where we started. So I'm going to double click on this, and that's going to take me to the Symbology tab. Symbology refers to how the layer is drawn. And right now it's just showing single symbol. That tells me where in the world it is. But you can also choose to display by any one of those attributes in the attribute table. So let's say graduated. And that's going to give a range. So it's going to show cooler streams in cooler colors and warmer streams in warmer colors. But I have to tell it which value to look at. And I want to say the average daily maximum temperature. And that's taking the highest temperature in each 24-hour period and averaging that over the July and August study period. So now I have to say classify, and it's going to show me here. So that's going by equal count or quantile, which means I have 5 categories, I have 95 sites, 95 divided by 5 is whatever it is, and it's putting that number in each one of these categories. I have other options here as well. I want to have pretty breaks. Give me things that make sense here. So 52 to 55, very cool stream. That might have actually been sitting in a cold water seep or a spring. And then super hot here, 75 to 77.7. And within here we have 5-degree breaks, which makes sense. So now I can say OK. And we can see some patterns on the landscape where down here we have a lot of warmer streams. Up here we have a lot of cooler streams. And I've done a lot of statistical work on this data set already. The best explanatory variable here so far is the gradient of the stream, meaning how steep the stream is. So if you picture a stream that's sort of flowing along flat, it's not flowing very fast, and it has a lot of potential exposure to sunlight, where a stream that's growing very steeply down the hill is going to have a lot less opportunity to slow down, be warmed up, that kind of a thing. But we'll be exploring patterns in this data set throughout the course. So we can see some variation here, and that's one of the reasons why I was looking at these valley depth models, where is there some reason why that there's a spatial pattern here, and that's one of the core questions of GIS. I've also doubled the sample size, so next year's data set is going to be twice as large, and maybe by the time we start this course, I'll have the 2020 data, which is super fun. So in any case, I was trying to explain the reasons why here, and there is some potential explanation here. We can see that these tend to be steeper, but this valley depth wasn't as good as the actual gradient of the stream, which measures how quickly the water is crashing down the hillside. So enough of that digression there. Let's move on to lines. Now we've established that vector data is made up of points, lines, and polygons. Points are physical locations or coordinates. If I right-click here, I can access the coordinates for that location where I clicked. There's the UTM northing and easting and the latitude and longitude. Likewise, if I look down here, I can see the UTM coordinates there as well as I move the mouse around the screen. So the point is the fundamental building block of both lines and polygons. If I zoom way in here, I can turn on my streams layer, and streams are lines, and these lines are defined by vertices, where if we zoom in here, every time this line takes a turn, there's a vertex. That vertex is defined again by coordinate pairs. So we have a physical location where this line turns, exactly the same as in mathematics, where a line connects two or more points. And this is a line segment from here to here. This is another line segment to the next place that line makes a turn. That line defines the stream, and that line is also derived from the digital elevation model. So water, if poured on the ground, will flow downhill, and as it flows downhill, you can say, well, this cell will flow into that cell, which will flow into that cell, which will flow into that cell, which will eventually all come into a line here. So that, we'll find out much later in the course how to do that, but that's where this line came from. And we can see a slight error here, and if we so choose, we can measure the distance between that physical location here and where that 10-meter stream is. So I say 10 meter because this is a stream defined by the 10-meter digital elevation model, which itself came from contour lines that were created decades ago. So it's not the very finest data set we could get. We're very soon going to have LiDAR data. LiDAR stands for Light Detection and Ranging, and is a three-dimensional laser scan of the landscape and the overlying vegetation, which is fantastic. We'll cover that later. But it gives a 1-meter resolution elevation model rather than a 10-meter resolution elevation model. That additional detail will give us a better idea of where that stream is, and we happen to know it's right there because that's where I was when I took the point. And we can check on that if we so choose by turning off our elevation model, turning on our air photo, and let's see if we can see the actual stream bed here. Once that comes in, valley depth goes away, and that's loading, loading, loading. There we are. So there's the stream. We can see how it's cutting through the canopy there, making a little bit of a turn. You can see there's a lot more detail here than is actually captured by that line. So that line is good and useful, but it's not perfect. So that's something to keep in mind. We can see another diversion here. Some of this could be because it's a very old data set from which this streams layer is derived, and part of it could be that it's moved. So streams do move over time. This itself looks like it may or may not have done, so it might have cut a new channel here, possibly an old channel here. This happens quite a lot with streams, especially on flatter ground. In any case, these are lines representing streams, and they're defined by vertices, points, defining each time that line makes a turn. There is no width to this line, though we can assign such a value to it if we added an attribute feature here. So that's not wanting to click here because I've not got that chosen there. That's just a quirk of the program. Now I can say, If I added a width here, I could add how wide that stream happens to be. And I can also measure that directly here if I'm curious. So there is a stream, and from bank to bank there, 5 meters in width. So now we see that a point is a physical location in space. A line connects two or more points. What is a polygon? A polygon is a closed feature defining area. So let's go ahead and turn on our watershed's boundaries here. There it is. That yellow line is a polygon. Polygon is defined in the same way that a line is, by vertices. So there's a point location there where that line or polygon boundary makes a turn. There's another point where it makes another turn, and another turn, and another turn. All of that together makes this feature, which is the watershed. So that is all the area that drains to this point location. So all the water is going to go down into that stream, flow downhill here, and end up at that point here where I've taken the temperature. So now let's go ahead and use our Identify Features tool. Click on that. That is the polygon that we're talking about here. So all of this area drains to here, and the sum total of all the activity and all the physical attributes of this watershed contribute to the temperature and other variables measured here. So we can see within this polygon we have a road here, two more side roads here, another road on the other side here leading out this way, another one coming out here and here. We have some beaver flowages here, some small ponds, and this is all defined by, again, the elevation model. And this here has me questioning, is this entirely valid? So I see beaver flowages here, and we can see the dam is built here. It wants to flow this way, and right in here is going to be the shallow edge of that watershed. So somewhere here is where that breaks. So the water is going to flow this way to the north, somewhere around here. And that's the old elevation model talking. So let's turn that off. Let's look at the elevation model here, and you can see how it's challenged here. So somewhere in here is where the actual watershed boundary is, and I'm interpreting that based on the air photo. So why am I telling you all this in the very first time that you see all of this data? I want you to not get taken in. There's an incredible amount of precision that we can have here. Drain acres, 1,184.34491018000 acres in this watershed, in this drainage area, which contributes to this point. There's a reason why this is a sort of preliminary analysis, because I can look at this air photo and see this water is going this way. This water is going this way. This watershed boundary is not entirely correct. There's a reason I'm not taking this to publication and saying these are my results, it's all done. I'm waiting for the LiDAR data, which is going to give a much higher resolution elevation model, which means I get a much higher precision watershed boundary, which is going to be much more reliable for saying this is the sum total of the effect within this actual watershed, which contributes to the stream. So I am going to be showing you some incredibly powerful tools that can summarize all of these attributes. I can say what is the valley depth within here, what is the total solar radiation here, what are all these different attributes which could contribute to this stream. Or later on when we're looking at deer data, where is the deer hanging out? Or where are the deer? Well, if we're looking at one color, where is the deer, singular? So all of these things, there might be errors in location, there might be errors in the input data, and you have to be able to look at this critically and say, well, this is a very nice, precise output. This can tell us a lot. I trust this boundary more than I trust this boundary. We have to learn to look at the weaknesses in the input data. If you have junk data in, you'll have junk analysis out. So we can still, of course, do the analyses, demonstrate them, and get most of the way there. But if something's going on in this back corner, I'm not entirely sure that this has any physical relation to that. So that is why I'm telling you this, that this is something that looks precise, and when you have very good input data, you can have very good analyses out. But there are limitations here when you have poor quality input data, outdated data, data from 3 years ago, where if last year something big happened here, if there's some landslide here and all that went away, got rerouted, huge beaver dams created here, all sorts of things that would modify the input and therefore modify the output. So, to sum up, we have points, lines, polygons. Points are physical locations and also define vertices where lines turn and where polygon boundaries turn. And finally, just as a reminder, rasters have cells and grids of cells or pixels where every one of these has one value. That value, if we look at it, is the, excuse me, I want to look not at that, but at this, and that is going to give me the elevation, band 1. That's all you get. Where if I look at this watershed boundary, thank you, now I have all this other information, and that attaches to an attribute table, which I can look at like so. I can look at all this data for all these points. I can look at all my notes, what every one of them is, what the average and maximum variations in temperature are. Those are all data that I've collected and attached to those points, to those locations, using the GIS. So these can be field notes that I then attach later on. I can type them in, or I can collect them automatically with a GPS, or with a phone, or with a tablet, or something else to that effect. So it is, in a way, putting data in its place. So you can collect all this data in the field, and then when you've got it all set to go here, you can look and see what patterns emerge on the landscape, what explains the variation that I see, and what are the physical relationships between different things on the ground, presuming, of course, that you have reliable input data for building that model. So we're going to be talking a lot about how much we trust our data, how to verify our data, how to collect data, how to improve it, how to update it, and also how to do analyses that tell us what are the relationships between these things on the ground, and then how do we access them? How do we get there? How do we drive there? There's some roads, how I got to every one of these sites. I can, if I'm using this on a tablet, turn on a feature that puts the physical location on there if the tablet has an onboard GPS or a connection to a GPS. So as I'm driving along the road, I can say, oh, time for a left-hand turn. I can expect to have a culvert here. I might slow down and see, oh, maybe the culvert's out, maybe we had a big washout. Driving along, driving along, driving along. Here I am, time to get out, time to walk. How far am I walking in here? I'm walking in 39 meters. That's how far I should expect to go. If I go much farther than that, I've probably gone too far. So GIS is incredibly powerful, but also incredibly sensitive to the quality of the input data. So welcome to GIS. Hope you enjoy your stay.